if we assume a closed loop, like we had with the wavelength that completed on itself, which I'm totally forcing to happen here. If we assume a closed loop, then we have 2 pi equals n lambda. So the circumference of this circle is 2 pi r. We're saying that that must be equal to an integer number of wavelengths. Then we have, this is what we get from, so this lambda here, so we have an integer number of wavelengths, and then so we have C equals, this C equals n lambda. We're going to say that lambda from the de Broglie wavelength is equal to h over mv. Plug that in here and we get 2 pi r equals n times the de Broglie wavelength, h over mv. We can rearrange this and we get that mvr equals nh over 2 pi. And we said that we're just defining h bar to be h over 2 pi. That's the name of that symbol, h bar. So if we assume a closed loop, then we can also say that L is equal to n h bar, or nh over 2 pi. So the angular momentum is equal to the energy level times, it's called the reduced Planck constant, h bar. So angular momentum is equal to energy level times number. When describing a quantum mechanical system, we use 4 characteristic quantum numbers. So we have 4 numbers that can give us the information that we're interested in about an electron. The first of these quantum numbers is called the principal quantum number. This is represented as n. It's the same n that we've been using. It refers to like the energy level. N can be any integer value. Equals 1, 2, 3, and so on. It defines the energy. That defines the energy and size of the shell. This is like the distance from the nucleus. A higher n value is further away, and it has a higher energy. All orbitals with the same n value are said to be in the same shell. The second quantum number is angular momentum. This is represented by an L. L ranges from 0 to n minus 1. Jumping ahead a bit, so this is the like letters that we talk about. So when we say that something is in the SPD orbital. So if L equals 0, we say it's in the S. L equals 1 is P, D, F. and then we have G, H. These actually started out meaning like spectral, principal, diffuse, fundamental. Like these letters actually came from words. But then when we realized what they actually were, we just started naming them with the alphabet. So after F, it's just G, H, 6 would be I. So this is to do with, it's more like the shape of it. So, yeah, it's also known as the secondary or the azimuthal quantum number. It specifies the shape of an orbital and divides it into subshells. So that's like what we have here. You've probably seen this if you've taken some upper level chemistry. So we have the S subshell, we have the S orbital. That's an S, that's like a sphere. We then have the P. P is, it's called the dumbbells. It's got a different shape than S. The D orbital, the D is these like clover shapes. So if we're talking about S, and then I don't even know what I would use to describe these. They're just confusing. So the angular momentum quantum number, the L value tells you if the L value is 0, you know that you're dealing with something that's in a sphere. If the L value is 1, you're dealing with the dumbbells. If the L value is 2, the clover, the D, like the D block, the L number is 3, I think, that's F. That is what, that's what the L is referring to. It's this shape. So N is referring to how far away, because each of these build on each other. So there's like the first orbital just has, the first one just has an S, then the second one has an S and a P, but they're like further out. So the N is like how far away each of these are from the nucleus, and the L is the shape of it. All of that would have made sense if you already understood it. I'm not sure if it actually clarified any understanding. Third is called the magnetic quantum number. This is M sub L. ML has values that go between negative L to 0 to L. So it has a value of 2L plus 1. We'll kind of talk about what that is. This specifies the orientation. So it's the orientation of the orbital with an energy of N and a shape of L. So this gets more specific about where the electron is. All of this I'm sure is sounding very abstract, but I'll work to solidify that once we've kind of gotten all the vocab. It's going to divide subshells into individual orbitals. And yeah, that's the number of them that we have. So let's do this. We have our L. We were given, so we have L. From the previous page, S is an L of 0. ML is going to be 2 times L plus 1. that means that, so 2 times 0 plus 1 is 1. P indicates 1. By the way, we just changed these to letters instead of numbers because there are too many numbers. So the fact that we're using these as letters is just to communicate more clearly. There's nothing significant about these letters. So P is 1. 2 times 1 plus 1 is 3. So then try to do D and F on your own. So for D, L is 2, and ML would be 5, F is 3, ML would be 7. Let's talk about what this means in terms of what we've got here. So we had that, I'm not sure if there's a good way to actually show both of these. But, so we said that L and we have ML. So this is L equals 0, L equals 1, L equals 2, L equals 3. For L equals 0, so for L equals 0, we said that ML was 1. We have exactly one so for L equals 0, ML is 1. For L equals 1, ML is 3, 2, 5, and so on. If we look at this, for L equals 0, we have exactly one possible orientation. It's a sphere. So this is, we'll call that ML is 1. Then we have our L equals 1. We have ML of 3. So we have ML of 3. We have 3 possibilities here. So going with what we used up here where we said that ML can be anywhere from negative L to positive L, I'm going to say that this is ML equals negative 1, ML equals 0, ML equals positive 1. Just going with that, I should say that's ML equals 0. But we have one possible ML value here, and we have 3 possible ML values here. Here, we have 5 possible values. So ML equals negative 2, ML equals negative 1, ML equals 0, ML equals 1, ML equals 2. That's what that is saying, so ML is 5. So the magnetic quantum number is saying how many possible shapes there are. So it's talking about the orientation.